Hello students, today we will be discussing law of mass action and derivation of the expression for the equilibrium constant for chemistry grade 10. The law of mass action is a fundamental concept in chemistry and it describes the relationship between the concentrations of the reactants and the products in a chemical reaction at equilibrium. If we recall back to what we studied in equilibrium and reversible reactions, we know that in a state of equilibrium, there is a constant forward as well as reverse reaction taking place, which means that the concentration of the reactants have an impact on the concentration of the products, and the concentration of the products also in turn have an impact on the concentrations of the reactant. They are in a constant relationship. It is based on the idea that the rate of a chemical reaction is proportional to the concentration of the reactants raised to their coefficients. The law of mass action states that the rate at which a substance reacts is directly proportional to its active mass. Let's take a pause here and think about what this means. The active mass, the more the concentration of this active mass, the more it is readily available in order to interact and react with other active masses to produce a product. A simple example, an everyday example of this would be that the more approachable and the more interactive you are in your class with your classmates, the more friends you end up making. In the same way, the more the concentration or the amount of active mass present, the more this active mass will react with each other to result in the formation of the product. Now, since an equilibrium reaction has a forward and backward reaction both happening simultaneously, the rate at which the reaction proceeds is directly proportional to the product of the active masses of the reactants, which includes both the reactants to produce the products as well as the products to produce the reactants. Mathematically, the law of mass action can be represented in the following equation. In this equation, we can see that this is a balanced chemical equation represented with the coefficients along with the reactants as well as the products. According to the law of mass of action, if we first break it down into a forward and backward reaction, the rate of forward reaction is directly proportional to the concentration of the reactants raised to the coefficients of the balanced chemical equation, which results in the rate of forward reaction being equal to the product of the concentrations of the reactant raised to their coefficients and the rate constant, also known as Kf. The rate of reverse reaction is identical to the rate of forward reaction in being directly proportional, however, to the concentrations of the products, this time raised to their coefficients. When further simplified, rate of reverse reaction is equal to the product of the rate constant and the concentrations of the products raised to their coefficient value. In a state of equilibrium, the rate of forward reaction is equal to the rate of backward reaction. That is, the concentrations of the reactants multiplied to Kf is equal to the concentrations of the products multiplied to the Kr. Therefore, when we rearrange the above equation, we can obtain Kf upon Kr is equal to the numerator comprising of the concentrations of the products raised to their coefficients and the denominator comprising of the reactants raised to their coefficients. This ratio of Kf upon Kr can then further be simplified and denoted as Kc, which is known as the equilibrium constant, and the above equation is the ideal equation known as equilibrium expression. Equilibrium constant, therefore, is defined as the ratio of the product of the concentration of the products to the product of the concentration of the reactants, each raised to the power equal to the coefficient in the balanced chemical equation. equilibrium constant is independent of the initial concentration of the reactants and is rather dependent on the temperature which maintains the equilibrium state.